Hey, it's Mr. Lum again, and we're going to be talking some more acid and base chemistry. And today we're going to be looking at weak base and a strong acid titration. Okay, which is a little bit different from last time, which we looked at weak acid and strong base titration. Today we're going to be doing a little bit different: weak base, strong acid. So here it is. What is a weak base strong acid titration? Well, let me draw a little picture of it right here. So what we're going to be doing is we have in our burette. Okay, so here is our burette full of strong acid. Okay, and this acid is, of course, strong. And in our beaker, we have some weak base. Okay, and then we have some kind of device in here, something like this, which is like a pH monitor. It's just constantly testing the pH as we add drop by drop of strong acid. And so we add our acid, and then we get down to our equivalence point, and then we add some more acid, and the pH starts to drop way down to here. So our equivalence point is right about here. This is our equivalence point. Now, the first thing we should notice about our equivalence point is that it is, well below 7. So our equivalence point has a pH that is less than 7. Okay? It has a pH less than 7. Now, a question is, why does it have a pH less than 7? Well, let's think of an example here. Say if we had an example of a weak base, like F-. Okay? And we titrated it with a strong acid, like HBr. Okay? Now what is going to happen is that F- plus HBr is going to be making, okay, since HBr is strong, it's going to be a one-way reaction. It's going to be making HF and Br-. Okay? So since it makes HF, this is like our acidic salt. So at the equivalence point, now remember, equivalence point just means that this ratio is equivalent. So if we had, say, 0.5 moles of HBr, and an equivalence point would be that the molar ratio is stoichiometrically equivalent. Okay, and when it's stoichiometrically equivalent, nothing is in excess, and we get HF. HF is an acidic salt, and that is why our pH is less than 7. Okay, it's an acidic at the equivalence point. And so we can write here pH is less than 7 because we make an acidic salt. Okay, so that's our first thing that is kind of important to understand. Now, let's get a few little definitions here. This right here is our, well, remember in our last one, it was VB for the volume of base added, but since we're adding acid, volume of acid added, this is called our VA. Now, this is about halfway point, and this is called our V half. V half is just half of VA. Okay? So V half just equals VA over 2. Okay? Now, if we draw a straight line, and my lines aren't that straight, but this right here is called our pH half. Okay, and we'll talk more about pH half. And if you remember from our last video, that with pH half you can calculate some things, some interesting things. And this we're going to call is our pH initial. It is the pH before any acid is added. pH half is how you get pH half. It's just half of pH half comes directly from where V half is on the graph. So V half is right here, and you just go to the y-axis and find out where pH half is. That's how you find pH half right here, straight from this graph. Okay? So important things to take away from this are where these things are located. Where's pH initial located? pH half, V half, VA. The equivalence point, okay, it's right in there. And why is the equivalence point less than 7 for this style of titration? And the reason is it makes an acidic salt. Okay, now let's look at some calculations and derive some formulas. So, our first one is how do we calculate Kb? So, we calculate Kb from pH half. So here is our titration, and let's pretend when we are adding our base that, well, in our beaker we have let's say we have 1 mole of base. Now at the equivalence point we would have 1 mole of HCl. But at half the equivalence point we have 0.5 moles of HCl. Okay. Now this is only going to be going one way. So since HCl is strong, it's going to 100% ionize, and that means this is going to decrease by 0.5. And that means 0.5 moles of this is going to react with 0.5 moles of this, because it's a 1-to-1 ratio. Okay? And that means this is going to go up by 0.5 moles. And this is going to go up by 0.5 moles. Okay? So how much, so what I'm trying to say is that we have excess amount of base in our solution at the time of pH half. So how much excess do we have? Well, we have 0.5 moles. Okay. Now this one, as usual, HCl is strong, so 100% of it ionizes, so we don't have any HCl left. And the amount of H base that we made is 0.5. And we also have 0.5 moles of this. Now we're only really interested in this one right here and this one right here. Now we're going to look at the other kind of equation in here. Now again, this is just a forward reaction. Now the other equation is the equilibrium reaction of the base, of the weak base ionizing or combining with water and forming H base, okay, or a base with a proton in there, the conjugate acid of this thing. So at equilibrium, we're finding that the base minus that we have is 0.5. Okay, we don't care about water because it's a liquid. And the H base that we have is 0.5. Now, this OH minus has changed quite a bit because we added all this HCl. So we don't actually quite know what our OH minus is because it's been changing due to the added HCl. But what we can do is we can take this equilibrium equation and make a Kb formula. We have to make a Kb formula because we are making OH. So Kb, as usual, is products over reactants, or in other words, H base times OH minus divided by base minus. Okay. And Kb, if we start plugging in some numbers here, say if we have H base is 0.5 and this is OH, and this is also 0.5. Okay, well, these are going to cancel out, 0.5 and 0.5. Okay, now someone might be thinking like, well, I wrote moles here and it should be molarity, and you're absolutely right, it should be molarity. Now this is happening in the same amount of volume of solution, so if we had 0.5 moles in 1 liter of solution, well, this molarity is going to be the same as this molarity. And so no matter what they are, they're going to cancel out like this. And what we're going to get out of this is Kb equals the constant of OH. Okay? But please remember that it's not just Kb equals any old concentration of OH. Kb equals the concentration of OH only at this point right here. Okay, again, Kb only equals the concentration of OH right at that point right here, and at that point right there is your pH half. Okay, so this is our V half, and I should say actually this is our pH half. Okay, and this would be our V half. Okay, and so our Kb equals the concentration of OH right here at pH half. Now, how do we change pH half into the concentration of OH? So how we do that is, if you remember, OH equals 10 to the minus POH at the halfway point. So all you have to do is change pH half into POH half. So how you can do that is just go 10 to the minus POH half, which is equal to 14 minus pH half. Okay? Or what we can say is Kb equals 10 to the minus 14 minus pH half. And that is how we derived this formula. Okay, and so this is the formula which you're going to use in order to calculate Kb. Okay, so what else can we calculate using our titration curves? Well, write this formula down in your books, and we're going to look at some more stuff and then do an example. So we can calculate initial concentration of a weak base. We use pH initial to calculate the OH concentration. Use the value of Kb that you found, and then solve for x. And we'll explain here. So remember our graph. Okay, our graph looks like, oh, that's ugly, but whatever. Right here is our, at this point, is our pH half. And way up here is our pH initial. Okay, so we're going to use that to help us. So before any acid is added, here is our formula for the ionization of our base right here. So our base is absorbing, is accepting a proton from water and therefore making OH minus. So we're going to make an ice table. Now, what we want to do is we want to calculate the initial concentration of the weak base. We want to calculate this. Okay. Now before this is put into the water, or before this accepts a proton from water, the concentration of H base and OH minus is 0. Okay. We know that this is going to shift to the right. So this is going to increase. H base and OH minus is going to increase. Now, we can calculate the concentration of OH minus. Okay? How you calculate that is from your pH initial. Okay? So I don't have a pH initial right here, so I'm just going to say that since this is going to increase, it's going to increase by an amount of Y. H base is also going to increase by Y because it's 1 to 1. Since it's 1 to 1 to 1, and it's shifting right, this is going to decrease by Y. So again, our equilibrium is going to be Y, Y, X minus Y. And if I were to come up with a KB formula, it's going to be something like this. KB equals Y squared, because Y times Y, products over reactants, X minus Y. Okay? Now, how do we calculate something like this Y? Well, we can calculate it from pH initial. Okay? OH, again, this is not just any OH, this is the concentration of OH, at this point right up here. Okay? So the concentration of OH is equal to 10 to the minus POH initial. How do you calculate POH initial? Well, if we have pH initial, it's pretty easy. So what we can do is we can just go, OH minus equals 10 to the minus, now POH initial is equal to 14 minus pH initial. Okay, and that's how we calculate the concentration of OH. How we calculate the concentration of OH at equilibrium, okay, which is equal to Y. Since Y is equal to this Y, we now know this, and we now know this. So we know this in our KB formula, we know this, and we know KB. Okay? Because KB is calculated from, well, we know that KB is equal to 10 to the minus 14 minus pH at half. So we can calculate KB. And we can use this to calculate Y. And, well, we can also use this same formula to calculate this Y. And so all we have is one variable, X, which is their question. Calculate the initial concentration of this. So you just solve for X, okay? And then you're done. That's the answer. Okay? So now that we know the basics of how to calculate initial concentration, we know how to calculate KB, let's do a question where we can do this all. Okay, so here it is. Monoprotic weak base is titrated with HCl. It says 25 milliliters of the base is used. So, let's draw a little graph up here. says 25 milliliters of base is used. That doesn't go on the graph. 21.2 milliliters of HCl was used to reach the equivalence point. That goes right here, because that is our VA, the volume of our acid used. 21.20. It says our pH initial is 12.2. That's up here. 12.200. Okay, that's right here. At 10.5, at 10.500 is the pH at 10.6 milliliters. Well, this number right here is half of this number right here. This is our pH half. So here's 10.6. Okay, and our pH at this right here is 10.500. Okay, so we kind of have our titration curve right here. So let's figure out what our concentration is of our, first let's find out what our Kb is, then let's find out what our concentration of our weak base is. Okay, and then we'll find out what our concentration of our HCl is. Anyways, let's go. Here it is. It is, well, our Kb is equal to 10 to the minus 14 minus our pH half. Okay. Or in other words, Kb equals 10 to the minus 14 minus 10.500, which is, this is going to be Kb equals 10 to the minus 3.500, and Kb equals 3.16 times 10 to the minus 4. Okay? That's it. So again, 3 sig figs. This is 3 sig figs right here. Sorry, 5.00 is 3 sig figs. Our answer is 3 sig figs. And that's our Kb. Now it says, let's calculate our initial concentration of monoprotic acid, weak base, sorry. So again, we're just going to go base plus water. So I'm making an ice table right now, and that's going to make H base, so that should be base minus, plus OH minus. Okay. Again, this is X. This is 0. Here's my initial, my change, and at equilibrium. Okay. This is going to decrease by a factor of y. And this is also, or sorry, this is going to increase by a factor of y, and this is going to increase by a factor of y. So let's figure out what y is. Or in other words, let's figure out what our OH concentration is. Okay? And our OH is going to equal 10 to the minus 14 minus pH initial. Or in other words, OH is going to equal 10 to the minus 14, and then pH initial is 12.2. OH equals, and I calculated this already, this is going to be 10 to the minus 1.8, and so therefore this is going to be 0.01 0.85. Okay, and so then I can take this number and its molarity. I can take this number and plug it into here. So this had to increase by 0.01585. 0.01585. And sorry. Now this is going to go decrease by 0.01585, and this is going to be then x minus 0.01585. Make my KB table, or KB expression, which is going to be H base, concentration of that, times OH minus, concentration of that, divided by our base minus. Okay, plug in our numbers. KB is, well, we figured this out earlier. So I'm just gonna write it up here. 3.16 times 10 to the minus 4, which equals 0.01585 squared. Okay, divided by x minus 0.01585. Okay, now then you solve for x. Okay, so multiply both sides by x minus 0.1585, and then move stuff around. Solve for x. I'm going to save a little bit of time, but x is going to equal, if we solve for x, x is going to equal 0.811 molarity. Okay, and sorry, and so that's our not the nicest of boxes that I've ever drawn, but whatever. So our base minus is 0.811. I shouldn't say x equals, because I'd say leaves it up for interpretation. I should be writing my base, my monoprotic base is 0.811 molarity. Now, I know I'm running really, really low on room, and I'm trying to think, should I try to squeeze in a quick calculation right here? Well, I'm going to try. It's going to be a little bit messy. But right in here, in this box, I'm going to try and calculate my concentration of HCl. Okay, so here it is. So if this is my base, and it's a 1-to-1 ratio, okay, because it's monoprotic, and HCl is, well, monoprotic as well, so it's going to be 1-to-1 ratio. I'm going to take my base, which is 0.811 moles per liter, and I'm going to times it by the volume of my base, 25 milliliters. Okay, or in other words, 0.02500 liters. Now I have, liters cancels, I have moles of my base. I then times this by 1 HCl. I know I'm writing very small. This says 1 HCl, and then is equal to 1 base, because it's a 1-to-1 ratio. And then I'm going to divide it by, so now after this calculation, I have moles of HCl. I then divide by the liters of HCl, which is, right here, 0.02120 liters, and that gives me moles per liter of HCl, or in other words, concentration of HCl, and that equals 0.956 molarity of HCl. Oh yeah. Okay, so finally, Kb was calculated. Oh, I messed it up and made it ugly, but whatever. Kb is calculated as 3.16 times 10 to the minus 4. We did it through this one. And we calculated our concentration, our initial concentration of weak base, which is 0.811. And then we use this number to calculate our concentration, our initial concentration of our HCl. Okay, using just straight up stoichiometry. Okay?